We present a unified simplicial method for simulating potentially non-manifold deformable objects whose components consist of various dimensions, that is, a mixture of 1D rods, 2D shells, and 3D solids. Standard elastic models focus on elements of a single type. Rather than construct an entirely new discretization, we develop a general coupling strategy to treat all possible connections among standard single-type models. We categorize the possible connections into three types: point connections in yellow, curve connections in gray, and surface connections in green. Here is an example simultaneously illustrating all the connections between simplices that are made possible by our method, including non-manifold and embedded connections. Our different coupling connections can be applied to a wide variety of application scenarios, as we demonstrate next. We begin with point connections. Here, we animate a simple toy ball on a spring colliding with the ground plane, with and without our approach. Similarly, rod-shell point connections allow us to animate several sticky hand toys of various lengths comprised of rods and shells. In this example, we use rod-shell and rod-solid point connections to animate several swimming jellyfish-like creatures. Next, we look at curve connections. This nylon frisbee example illustrates three possible distinct behaviors for three geometrically identical meshes. On the left, the frisbee has no embedded rod. In the middle, a stiff rod is embedded into the boundary without rotational coupling and then rotated along the red region. On the right, the same rotating rod is rotationally coupled. This example opens and closes an umbrella comprised of elastic shell material with metal rods embedded through it. Similarly, here we have a tube of elastic cloth with and without elastic rods embedded through it in a spiral pattern to form a children's toy tunnel. Here the same tunnel is compressed and then allowed to spring back up. Different connection types can be combined to form more complex structures. This cartoony anglerfish consists of a solid body, fins comprised of shells, and a rod-like appendage with a solid spherical light on the end. Lastly, face connections allow embedding shells into solid objects. A natural example is to embed stiff shells into a softer solid volume to form a sandwich-structured composite. The remainder of this video provides supporting didactic visuals for points raised in the paper. In the following examples, we will color-code the components as shown here. In particular, vertices displayed in red have their motion prescribed in advance. First, we consider point connections, beginning with a rod-shell point connection. Next, we see the remaining four types of point connections. There are four possible curve connections. We first illustrate a rod-shell connection in which the rod is embedded into the shell. The shell with embedded rod is released under gravity. Note the differing behavior as the stiffness of the rod is increased. In a similar scenario, we illustrate the effect of bending forces between the shell and embedded rod by prescribing the rod to rotate. Next, we illustrate the remaining three curve connection types, which behave in similar ways. Finally, The simplest type is a surface connection. The only possible example is a shell embedded into a solid. To illustrate the importance of our incremental angle update for large rotations, we consider an embedded rod in a shell while observing the motion and corresponding energy plots. Specifically, we rotate the rod with constant velocity while initially holding the shell fixed, and then release it while continuing the rod's rotation. With a naive, direct update, we observe unphysical, discontinuous jumps in angle as the deformation wraps past pi. Using our incremental update, the proper angle is computed, leading to correct motion. Finally, we demonstrate using our method with a stiff connection to form a smooth blend between a shell and a solid. We show 4 simulations comparing a pure solid object, its pure shell counterpart, and the same shape discretized as half solid and half shell in 2 different orders.